Okay, so what in the world does a guitar string have to do with the deepest mysteries in quantum physics? Well, you might be surprised. The answer involves a number that seems to break the rules of reality, and our journey to figure it out doesn't start in a lab. It starts with a simple vibration.
At the very heart of this puzzle is this number, 2 times the square root of 2. Now, in experiments that test a fabric of reality, this value keeps showing up. And here's the crazy part. It breaks what we thought was a hard limit, kind of like a classical speed limit of 2, for how connected two things can be. But quantum mechanics just blows right past that limit. This new, higher boundary, that's the famous Chorelson bound.
So, the big question is, where does this number even come from? What's so special about the square root of 2 that it gets to define the absolute edge of quantum weirdness? Honestly, it feels, well, a little spooky. But the answer, or at least a really powerful way to see the answer, comes from a place you'd never expect. So let's just put aside all the complex quantum stuff for a minute, and let's pick up a guitar. We're going to see how its strings can actually show us a deep physical truth. So let's set up our experiment. Don't worry, we're not about to get lost in a sea of complicated math. The goal here is to build a really clear physical intuition for what's actually going on under the hood.
The whole process is actually pretty straightforward. Imagine Alice and Bob each have a guitar string. First, they tune them so they're perfectly identical, so their vibrations are linked. We'll just call this shared vibration lambda. Next, they each pick an angle to place a sensor. Then, at the exact same time, they pluck the strings and take a single instantaneous snapshot. All they write down is the amplitude, how loud or how far the string is vibrating at that one moment. That's it. That's a single trial.
So what is that snapshot really measuring? Well, it's just simple geometry. It's a projection. Think of the shared vibration lambda as an arrow. Alice's measurement is just the shadow that arrow casts onto her sensor's line of sight. If the vibration arrow is lined up perfectly with her sensor, she gets a huge reading, a loud note. If it's at a right angle, the shadow is 0, and she gets silence. It's pure, simple geometry.
Okay, so one trial is simple enough. But what happens if we do this thousands and thousands of times, with the vibration starting at a totally random direction each time? Well, as you're about to see, all those individual little data points start to build a surprisingly beautiful and very revealing picture. To see the pattern, we create what's called a guitar correlation grid. Think of it like an old-school oscilloscope screen. For every single trial, every pluck, we plot Alice's result on the horizontal axis and Bob's result on the vertical axis. Each pluck just becomes a single dot on this grid.
And look what happens. As the dots from thousands of plucks pile up, they don't just form some random cloud. No way. They trace out a perfect tilted ellipse. This shape isn't some accident. This shape is the correlation, made totally visible. The amount of tilt is set by the angle between Alice's and Bob's sensors. We've literally turned a statistical idea into a geometric shape.
I love how the author of this model puts it. The connection isn't hidden in algebra. It's right there. You can see it. It's an ellipse. That simple geometry of projection is what's creating this beautiful shape. The physics is literally drawing a picture for us.
All right, now we get to what might be the most important part of this entire idea. We have this beautiful, continuous data, the ellipse. But see, real quantum experiments, the Bell tests, they don't work like that. They record a simple binary thing, a +1 or a -1. It's a click or no click. And as we're about to see, the way you choose to translate that rich, continuous note into a simple click, it changes everything. So, we have a choice. On the left, there's the equal weight method. All we care about is the sign. Was the vibration positive or negative? That's it. We throw away all the rich information about its loudness, its amplitude. But on the right, we have a geometry-preserving method. Here, louder notes, the ones with bigger amplitudes, they actually have a bigger impact on the final numbers. This method respects the shape of that ellipse we discovered. And this graph, wow, this graph shows you the massive result of that choice. The blue line, that's what happens when you just count the signs and ignore how loud the note was. Check out the 45-degree mark. The correlation is 0.5. But the orange line, that shows what happens when you preserve the geometry. At that exact same 45-degree angle, the correlation is suddenly 1 over the square root of 2. Let that sink in for a second. We are measuring the same physical system. The only thing we changed was what information we decided to keep. And with that one insight, we can finally connect all the dots and get back to our original mystery number.
It turns out the answer has been hiding in plain sight this whole time, right there in our old high school geometry books.
You see, the standard quantum experiment that actually tests this stuff, it's called a CSHS experiment. It doesn't just measure at one random angle. To get that spooky 2√2 result, it very cleverly combines measurements at a very specific set of 4 angles. And as you can see, our critical 45-degree angle is right there in the mix.
And this is the key. That number we saw in the graph, 1 over the square root of 2, it's not some weird quantum constant that fell out of the sky. It's just the cosine of 45 degrees. It's Pythagoras. If you have a right-angled triangle with 2 equal sides, that's the ratio. It's just pure, simple geometry.
And that's the whole magic trick. That's how it works. That spooky quantum limit of 2√2 is nothing more than the result of adding and subtracting the correlations from those 4 specific angles. When you plug in the simple geometric value of 1 over the square root of 2 for each of those measurements, the math just works out perfectly. The spooky number isn't spooky at all. It's built brick by brick from simple, visible geometry.
So after all of that, what does a simple guitar string really teach us about the quantum world? What's the big idea here?
Well, the biggest takeaway is this. The square root of 2 isn't spooky, it's geometric. It just comes from projection, from shadows. But maybe the more profound point is that our measurement choices matter a lot. The act of turning a continuous wave into a discrete click isn't a neutral act. When we throw away information about the wave's loudness, we fundamentally change the reality we end up seeing. It's a powerful reminder that sometimes what we choose not to see is just as important as what we do.
Now, to be super clear, this guitar model isn't a perfect theory of everything, but it leaves us with a really fascinating question to think about. Could the famous strangeness of quantum mechanics be, at least partly, a story about measurement? A story not just about reality itself, but about how the continuous strength of a wave gets translated into the discrete clicks of our detectors. It suggests that maybe, just maybe, the mystery isn't only in the song the universe is playing, but in how we choose to listen.